In this paper, we present an approach to separate the effects of global illumination and projector defocus for recovering geometric and material properties of a scene. Consider this scene. It consists of a clay pot, a wax candle, a poly-resin bust, a marble statue, and a V-groove. The scene has a significant amount of global light transport in the form of interreflections and subsurface scattering. Our experimental setup consists of a camera and a projector co-located using a beam splitter. The co-location is done only to ensure that we get complete, hole-free depth maps. The projector illuminates the scene with a shifting striped pattern. The scene radiances are recorded by the camera. In this example, the projector focal plane is behind the scene. Notice that the pattern on the background is better focused as compared to the clay pot in the foreground. The depths for the candle, the marble statue, and the V-groove concavity are overestimated due to subsurface scattering and interreflections. Also, the interreflections between the folds on the statue and the bust result in incorrect depths. We present two algorithms for recovering scene depths in the presence of global illumination. The first algorithm requires two focal plane positions of the projector. For example, we may use one focal plane position behind the scene and one in front of the scene. Notice the different amount of blurring on the same object across the two focal settings. The depth estimates are correct even in the presence of global illumination. The second algorithm requires multiple focal plane positions. This is similar in spirit to the shape from camera focus algorithms, requiring a sweep of focal plane across the scene. The depth estimates in this case are more robust. Here we show a comparison of our two depth recovery algorithms and the existing single plane algorithm. Next, we consider the problem of separating the direct and global components of light transport. Nair et al. Used high-frequency illumination, such as a checkerboard pattern, to perform the separation. However, for a scene with large depth variations, there is the additional effect of projector defocus blur. Notice the different amount of blurs on the pot and the background. Here the focal plane was placed behind the scene. Due to defocus blur, the direct component was underestimated, and the global component was overestimated in the front portion of the scene. Here the focal plane was placed in front of the scene. Now, the direct component is underestimated, and the global component is overestimated in the back portion of the scene, especially the background wall. Here we show the results of applying Nair et al.'s separation algorithm for different placements of the focal plane. For scene points distant from the focal plane, the separation recovered is incorrect. We present two algorithms for separating the direct and global components in the presence of defocus blur. The first algorithm requires multiple focal plane positions. Here we show the direct and global components obtained using our method. Notice the high global component on the candle and in the V-groove concavity, and the low global component for the clay pot and the background wall. The second algorithm requires only one focal plane position and a depth map of the scene. Here we show a comparison between Nair et al. And our two separation algorithms. Next, we consider a scene made of organic materials, such as vegetables, plants, and flowers. Once again, this scene exhibits both subsurface scattering and interreflections. Using our method, the peppers are correctly estimated to be in front of the pumpkins. The interreflections between the eggs don't adversely affect the depth estimates. Here we show the results of applying Nair et al.'s separation algorithm for different placements of the focal plane. As before, for scene points distant from the focal plane, the separation recovered is incorrect. Here we show the separation recovered with our algorithm In summary, we have presented an approach to separate the effects of global illumination and defocus blur using high-frequency illumination. We used our approach to derive two algorithms for depth recovery in the presence of global illumination and two algorithms for direct global separation in the presence of defocus blur.